good lunch. I'm actually happy to be here and fortunate to have the chance to deliver this presentation. Yesterday it was a little bit frustrating when I realized that it's going to be cancelled. But anyhow, we are here and I'm glad to do that. As you heard, I come from the Technion, Israel Institute of Technology. My background started as a chemist, physical chemist, then I moved to soil science, physical chemistry of soil and environmental systems, and with time I moved also to water physical chemistry, being the head of the Department of Water and Environmental and Ag Engineering at the Technion at Civil and Environmental Engineering. I got exposed to many issues related to soil problems, water problems, and in the last year I'm heading the Groundwater Research Institute, and then indeed I even enlarged my scope of interest in many water issues. But today I'm going to focus on water scarcity and food security challenges because I believe they go together. And I will try to do things simplified as possible. Here and there we will go into a little bit more technical details, but altogether we'll try to talk more general about the issues. I will start by showing you and that there are different options to show the water scarcity problems in the world. What you see here is that generally people can look at them at either physical water scarcity problems, and then they talk about not having enough water. And as you can see, the regions here, where I come from, or regions here in South America, or many regions in China and India and Asia. When we talk about physical water scarcity, it means that there is not enough water to support the demand of what people would need. And I will not go into the numbers. But what is important to realize that there are regions in the world which are under what would be considered economic water scarcity, like what you will see here in this part. And when we talk about economic water scarcity, it means there is enough water in the region. But still, a big part of the water would not be available for people. So they will suffer from problems that you will meet in places where you have physical water scarcity. And indeed, these problems can be solved either by technology management and always policy and economically driven solutions when we talk about the physical problems. But when we talk about the economic water scarcity, again, it's very important to remember that when we have that problem, it can be solved either by political involvement, by economical involvement, and then we have to go, after this involvement will go in, then we'll have to go to the technology. The result of both, whether would it be physical water scarcity or economic water scarcity, a big part of it will result in food problems and poverty and hunger. It will result in sanitation problems as well, which I am not going to refer to. All these colors, starting from yellow and going into the red, depict regions of hunger. And again, you can see regions of hunger where you have economic water scarcity, or regions of hunger where you will have physical water scarcity. Preparing for this course and meeting, I was asked to send an article which represents these problems, and one I was choosing is an article which was published by the group of Jonathan Foley from Minnesota University, and it's talking about solutions for a cultivated planet, closing yield gaps. And actually, by making a big survey over the whole world, they came up with results which really show that there are very large gaps in yield production, that by working properly and by addressing them, we can really close a big part of the missing food in the world, or what they call closing the yield gaps. I won't go into the details on what's written here, but all together, what they say, that they analyze solution to these dilemmas, the dilemmas of hunger and food production, showing that a tremendous progress could be made by halting agricultural expansion, closing yield gaps on underperforming land, increasing cropping efficiency, shifting diets, and reducing waste. Together, these strategies could double food production while greatly reducing the environmental impact. And this is what they have done, is just surveying what's happening in the world. What I will try to show you from my understanding of things, how, to my understanding or our understanding, and bring you examples from Israel, things can be done and the way that we will be able to close the gaps. From another point of view, and these declarations here or statements here are made by another professor or doctor from the group, from the same group, now working with the FAO, and clearly he would state that world food demand will almost double by 2050. Without an increase in water productivity, which is very important for food production, or significant reduction of the demand of food, water consumption in the year 2050 may double as well. So we will need a lot of water if we don't do something and don't act properly. The world is thus exposed to progressive and critical increase in water scarcity. Indeed, we have also to consider the climate change, and I will not go into projection of climate change. I heard some people here that are very much involved with it, but even without big climate changes, we are going to go into big problems. And then the issue of food and water security, they are two faces of the same coin, and this is what I will try to show and demonstrate in this talk. But before we talk about water and food, I come from soil science, and I think that soils is part of it. Actually, this figure shows you what is happening with the soils in the world in terms of their degradation to human activity. And again, we will not go into mechanisms and descriptions why. But what you see here is a map which shows degraded soils. Would it be, if you look at that color, or even at a more brownish red color, as you go into the reddish color, the degradation would be more severe. And the degradation could be due to many of our activities in the world. And the issue that we have more and more degraded soils is very bad for the issue of food production. I will try to make it clearer a little bit later. But you have to remember that soil is a big component, and available soil and fertile soil is very important for food production. Well, I'm magnifying the map to show you that the reddish colors are pretty dominant in our region, that I will focus later on a little bit more. Well, we are all aware that the population is growing exponentially, and with the growth of population, all problems, environmental problems, water-related problems, air pollution problems are also growing exponentially. At the same time, since we talk about food production, it's interesting to see how the sectorial demand for food, for water, has changed in the last 100 years. As you can see, about 110 years ago, 95%, the green color, of water was required for agricultural production. Situation today is that 71% are still required for agricultural production, or 81% for food. And the other 30 are required for industry and municipal use, or our homes. Again, these are world averages. When you go to some places, undeveloped places in the world, you would realize that 90% of the water is needed for food. And the consumption for industry and the domestic consumption will be much, much smaller. And actually, since we know that food demand is going more or less to double, it means that we will need also a lot of water to sustain this food demand. And as you can see, this water will compete with all other sectoral requirements of water. At the same time, we have to remember that food scarcity is going to grow. And here there is a little bit different definition of food scarcity from the one that I was showing you in the first slide. In this case, food scarcity is defined as the amount of water per capita less than 1,000 cubic meter per capita. There are many regions in the world where there are less than 1,000 cubic meter per capita. I believe in the States you have also some places. When you look at the average of the States, it's quite different, but it's not fair to look at the average of the States when you have the northern countries and the southern countries like Texas and Nevada and parts of South California. Altogether, water scarcity means that people have less than 1,000 cubic meter per capita per year. And the situation is such that today we have about 300 or 400 million. These are the amount. These are the in terms of billions of people in the world, about 300-400 million of people under water scarcity. Projected for 2050, we are going to have about 1.4 billion people under water scarcity. And then if we have water scarcity, much less than needed, but still a big demand for water for food production, then the problem is going to be even bigger, just because of the fact that water scarcity is going to grow. And again, the question is, under which climatic models are we talking? Would it be more severe, less severe? But altogether, the numbers are referring here to some kind of medium situation, not to the severest climatic projection or to the less severe climatic one. And indeed, as you can see, there is a very strong interdependence between the environmental demand, population growth, food need, and water need. One of the classical ways that we are used to show to our students what is happening in terms of food production and in terms of soils productivities in the world is this kind of demonstration, sometimes also called the poverty trap. The poverty trap tells us that in many regions in the world, looking at the situation in Africa or South America or parts of Asia about 50, 60, 70, 80 years ago, when they wanted to produce food, they could do it with no problem. The soils were fertile enough, and then they started to grow more and more with little attention to returning organic material, to supplying nutrients. As a result, they exhausted the soil ability to produce food, and they went into kind of a poverty trap. Whether it be governments taking care of, or people helping them to understand that it is important to return back to the soil which you are taking out, things would be different. But the fact is that in many regions, we have this kind of poverty trap. So classically, this is what we would show our students is happening in terms of losing the ability of the soil to produce food. But now, let's remember that today, in addition to the poverty trap, we are also going into big problems of water scarcity, and then the situation will be even much worse, because not only the soils are degrading, we will not have enough water to sustain the food production, so the problem will be indeed bigger. This map is trying to show you on the left the changes that the world was undergoing from the year 1700 until the projected situation to the year 2050 in terms of land used for agriculture. Please have a look at the agricultural land in brown and the extensive grassland in yellow, but specifically in brown. And you can see that the dominancy of this brown color is increasing and increasing in many regions in the world. So this is the aspect of the land that we are using for food production, and again, more fertile, less fertile. But the other issues to look at is the issue of what's going on in terms of the ecological changes. And one of the measures to look at ecological changes is to look at biodiversity. I will not go again to teach you about what's the meaning of biodiversity, but roughly thinking, we, the ecologists, believe that we want to sustain biodiversity in the world as much as possible. To have a diversity in everything that moves and lives in the world, which is very important ecologically. And we will not go into explanations why. The issue is that with time and with development and our activity, and our agriculture activity, there is a high impact on biodiversity, and many species disappear. So one of the criteria of the change, the biodiversity changes, is to look at the impact of many species and describe it percentage-wise. For instance, high impact would be abundance of less than 25% of what used to be before. So again, when you look at the world maps from 300 and something years ago to the projection, you can see with time, and let's just put it up and see that the black color, which means very high impact, or the red color, which is high, medium impact on biodiversity, are going and increasing. And this is going together with the agricultural activity. The point to make here is we need to produce food, and that's very important. But at the same time, we have to remember that when we produce food, any of our activity, not only food production, but any of our activity in food production will also have ecological aspects and will affect also biodiversity, which in the long run we would like to minimize that effect. And the question, how can we do it? I will not go answering this question, but one of the points is if we do want to produce food, maybe we should do it in a smart way and not extend the acreages that are used for food production, but on the same land, be effective in producing the food and leaving a lot of free land, which is not overloaded with chemicals, so that we will not affect too much in the long run the biodiversity or the ecological aspects.
I have a question. In the map, you can see that the non-productive land in the African continent does not have much impact on the biodiversity. How does that relate? So the white region in Africa,
yeah, well, it
says low impact. So how is that related?
It's low impact because these are agricultural lands. But the question is, what is the input on the agricultural land? The input on the agricultural land in Africa, in terms of chemicals, in terms of fertilizers, is much lower, and therefore the food production is much lower. Also, the ecological impact is lower. So that's one good thing about what's happening in Africa. Right. But then you ask, how efficient are they in food production? Very non-efficient. Okay,
it seems like there's a relation between agricultural productivity and impact on biodiversity. That's why where there's no agricultural productivity. I mean,
there are places. Well, we don't have too much for such a question, but there are places. When we talk here about agricultural land, it's very general description of agricultural land. It can be very intensive and it can be very extensive. So this is the key answer to your question, okay? Now, another way to look at food production and water is the area that is used for harvesting. And we can look at irrigated land and we can look at rain-fed land. And as you can see, the proportions relevant about 10 years ago and projected for 2030, it's about 17 to 80% of the land is harvested under irrigation, and 80+ % is harvested under rain-fed, which means no irrigation, just we use the rain, which is falling on our soil, stored in the soil, and then the plants can use it. There is also the issue of biofuels, which I will not go into it, but biofuels, which are mainly used for growing on rain-fed, they are completely used for production. We don't have time to discuss that, but that's something to remember. Now, we can also analyze the situation, not in terms of land use, but in terms of water use. And the proportions are pretty similar. Again, here we talk about the amount of water used for food production, and you could see the blue. We call this kind of water blue water. Blue water is the water that we are pumping from our reservoirs, from our aquifers, for our streams, sending it to our homes or to the farmers to use for irrigation. This is called blue water. Green water is the water that is stored after the rain in the soil. So you can see again, proportion-wise, less than 20%, closer to 70% of the water that is used in the world for food production comes from blue water, which means from the resources which we have to pump. These are the resources that compete with our home use with our industrial use. These are the resources that we talk about, okay? The green water is the water that is stored in the soil after the rain. And as you can see, it has a very important role because it's more than 80% of the total water used in the world for food production. But then, when you ask yourself percentage-wise, or would anybody have a guess how much of the total food production in the world, in terms of percentage, comes from the blue water, from irrigation? Close to 45%. So that part of 17% of the whole water that is used for food production is producing close to 45%. We are coming close, almost half of it. Half of the food production comes from irrigation, which means that if we really want to be very efficient, and maybe if we would like to have some of the rain-fed areas free for other activities, if we would be much more effective in growing with the percentage of irrigation, maybe we can do a lot. But at the same time, we should remember, as long as this is not done, and a big part of the food production in the world is based on the rain-fed area, we have to take care of the soil. We have to conserve it. We have to teach the farmers to do much better, because they can do much better. And most farmers in Africa, they produce the food here, but with very low input into the soil, so they could do much better, and then maybe the proportion of the total soil used for food production will be smaller, and then the other part of the land could be free for other sectorial uses. Now, there are also other aspects, and it's a little bit to make it a little bit more popular, but very relevant, and to see how much do we use and for what. So as you can see, and this is not the first one is not to convince you to become vegetarian, but it might be a good idea. Water needed to produce 1 kilo of wheat would be roughly 1,000 liters. For 1 kilo, we need 1,000 liters. Okay? 1 kilo of meat, beef, would be 15,000 liters. By the way, pork would be half of it. It's not kosher, but pork meat would be half the amount of beef meat. But still, as you can see, 15 times or 7 times more water needed for meat than for wheat. And then daily requirements of water for drinking, we need a few liters, but domestic needs altogether, depending on the standard of living in the world, from the very poor regions, 20, 30 liters, up to 300 liters, where the standard of living is very high or it's very hot and you need to use water for many, many other reasons. Food, roughly, depending on what you eat, would need world average between 2,000 to 3,000 liters of water a day for food. Statistics shows that the average for the US, the statistics I have, for food would be more than 5,000 liters. But roughly in the world, and again, since it's average and we have very poor regions, roughly in the world, with 2,500 liters of water, we can produce food for one person for 1 day. Or, alternatively, with the same amount of water, we can produce 1 liter of biofuel. So that's to give you the proportion between the importance of water for food and water for biofuels. And I'm not going to preach here what's more important, just to show the numbers. Let's go ahead. This is a figure I got from a friend in Holland. This is the way the Dutch people look at it. But let's start with the left part. The left part of the figure is telling us how much land do we have per capita today. And these are the numbers close today, which in terms of hectares per capita. Today we have something like 0.21 hectares per capita arable land for food production. Situation 50-something, 60 years ago was that we had 0.51, which means a decrease, a very, very significant decrease of land per capita for food production. And then comes the question, what can we do with this land? And we are in a very, very diverse world, You need 2 square meters for 10 roses. People need roses in the world as well. Not everywhere, but this is what you can figure out. 6 square meters for a weekly portion of Dutch weed. I got it from a Dutch friend. Dutch weed, this is what they like to smoke in Amsterdam. You need 100 square meters for a vegetarian meal, and you need 1,000 square meters for a meat meal. And again, not only more water needed for meat, also area needed for meat, because you need to produce food for the meat. You need to have space for the animals to go around and much more. And again, I'm not trying to preach vegetarian. I like to eat meat, but proportions of water needs and land needs for food have to do also with what kind of food we are going to eat. And I'm not going indeed to go into this issue, but we should have this kind of thought in mind as well. And indeed, when we consider global climate change, there are again projections, and these are models, and I will not go into them, but the rough projections tell us that because of the global climate change, of the growth in heat, but also the big changes in extremes, we may go into more severe extreme situation, which we will have in some regions. Maybe the average of total water that we'll have annually will remain the same, but we will have larger extremes, which means we may have a few years of very severe drought, and then a few years of very high rainfall. In some regions, like our region, when you go into such conditions, both would be very bad. If you have too much rain, like we had this year, on October, normally on October we will have about 20-30 millimeters of rain. We talk millimeters, not inches, but 1 inch is 25 millimeters, roughly. And this year we had in October 200 millimeters, which is a lot for us. And you know what's happening with the soils we have in our regions when we have 200 millimeters instead of 20? Most of it will run to the sea, runoff. Because when you have the type of soils we have in our regions and you have too much rain, water will run away. So when we go into extremes and heating, what is projected that in many regions in the world, and again, the ones that will be very much affected according to these models, India, big parts of Africa, big parts of South America, and also big parts of south part of the North Americas, then you will have a big change in agriculture, negative change in agriculture. Let me go to this slide. This slide was prepared by an expert from IFC. IFC is the International Finance Corporation, World Bank. I've met him in a conference that we invited him to Israel about a few months ago, Anup Jagwani, and he analyzed the situation of food production in the world, being commissioned by the World Bank. And again, he's showing very similar trends that I was showing before. That altogether, global water production by sector for food would be 70%. Domestically, we need around 11%, and industry would need 19%. But again, depends which area of the world you are. The big issue as the food demand is increasing, there is limited availability of agricultural land, and we have very big water withdrawals. And his idea is, again, very similar to what the group of Minnesota comes out, that agricultural growth has to come from higher yields. It's not that we will have more and more land to work on. If we don't do it efficiently, we are not going to do a good job. And it has to come mainly from higher yields, from the same area of land, but with more efficient use of water and other inputs. It's not only water, it's indeed the nutrients, for instance. Being involved with the World Bank, he knows that this is not enough. And having a discussion in his presentation, and I will focus on it later, indeed we need to be more efficient technically in terms of water use efficiency, nutrients use efficiency. But one of the big issues is also how do we bring this knowledge to many regions in the world where the knowledge is not less important than the technology. Now we go back to that publication of the Foley group from Minnesota, where I started with it and now I go back to it, where they were talking about closing the yield gaps, and indeed they are showing the yield gaps in the different regions in the world, and where they project that we can increase the yield gap. Roughly on the way they have analyzed it, they talk about potential increase of 58% just by trying to help the farmers increase the yield gap. And then the question is, how can we do that? They just speak in very general terms: be more efficient, use water efficiently, use nutrients efficiently, and they show that there is a problem, and they really show that it's possible to do it. Because when they talk about increasing the yield gap, they have just compared. People grow wheat very successfully in the US and Israel and areas of China. Why not do it in Africa? Why not do it in South America and other regions where they don't do it? So they came to the idea just by comparison. They didn't bring solutions how to do it, but they say it's possible, because if they do it there, so good, why won't you do it? And indeed, here I will come and give you a few examples how we did it in Israel. One way to show it is to look at what Professor Yoav Kislev, he is a water economist. And what he is showing is the change in amount of water, cubic meters per capita per year, used for agricultural production, the blue line in Israel. And you can see that in the year 1958, we have used 517 cubic meter per capita for food production. In the year 2008, when he published this article, we have used 170 cubic meter per capita. Total amount of available water was reduced. Increase of population was by a factor of 3.5. And what you can see that we continue to produce the food, and actually the food that we produce today and the quality of the things that we produce today is much higher, but we did it 3 times less water. But more than that, when you look into what is the water that we use in Israel today for food production, out of that 170 compared to the 517 here, half of it is reclaimed wastewater, not fresh water. Which means that today we produce in Israel the food for everybody, compared on the basis of fresh water only. We produce it with 85 cubic meter of fresh water, and the other half is reclaimed wastewater. So it's not only that agriculture became very intensive and very productive and very efficient, but also the type of water that we are using. We are replacing part of the fresh water, and instead of using fresh water, we use reclaimed wastewater. And indeed, you ask yourself, how can this be done? And this can be done by many technologies, which I will briefly mention. But before I will go and mention it, let's see the situation in different regions of the world. Again, the same figure that you have seen here. Amount of water, cubic meters per capita per year for agricultural production in our neighboring countries. So you can see here Egypt, Greece, and some other countries where they use not the amounts that we use, but much, much higher. And if you go to South America, the numbers will be even higher, because they also grow a lot of meat. But interestingly, you can see on the lower part, where you can see Israel, but together with Israel, you can see also Jordan, and you can see also Cyprus. Again, it's a little misleading. Indeed, we see much lower numbers, 100, 150 cubic meters per year per capita. The next question you should ask, do they produce enough food for the nation? Indeed, in Israel we do it, and we even export. Would you ask the same for Jordan? No. But they don't use more than that because they are very limited in the amount of water that they have. I will now try to focus on an example and an analysis that was done related to our region, which is called also the Middle East North Africa, MENA region. This analysis was done by a group of experts called Future Water Report, and they were commissioned by the World Bank. The report was issued about 2.5, 3 years ago. And what you can see from here is that they declare that the region, the Middle East North Africa region, can be considered one of the most water scarce regions in the world. Large-scale water management problems are already apparent in the region. Aquifers overpumped, water quality deteriorating, agricultural consequences, human health, and more. And then they come up with a description of the problems and also with a description of solutions. This figure, based on their analysis, is showing what happened in the past and projection into the 2050s in terms of water demand. Water demand is in the upper part of the figure. The units here are cubic kilometers per year. Year 2000 is here, year 2050 is here. And you can see that the big demand for water would be the demand for irrigation, for food production, indeed. Then you can see a very significant increase in urban demand, water for people, because the population will grow and also standard of living will grow. But then they have analyzed the situation of the unmet demand. How much water will be missing for producing the food for our homes? And you can see that the unmet demand roughly today, in terms of the unmet demand, is that color here, the purple color. The blue colors are showing the available water in the streams and the aquifers and the surface water. The purple one is showing us the unmet demand. So you can see that the unmet demand here on the negative part is something like 15%. But the unmet demand in the 2050 will be about 55, 60%. And the question is, where do we take in the region here, in the MENA region, this water, which will be mainly required for food production? And then they come up with a figure, and I will try to explain it as clear as possible, which shows the amount of the unmet demand and how, with different approaches and technologies, and giving also a cost, a marginal cost for each approach, how can the unmet demand be taken care of? And I will not go into all the measures that they are presenting, but I will give you one or two examples which are very relevant. Again, this is the average unmet demand. Again, when we go to the projection of global change, they didn't take the severe scenario, they take an average scenario, and the unmet demand would then be about 260 billions of cubic meters per year. Now they project that about 54 billions of cubic meters, the blue color here, can be taken care of by a marginal cost of a few cents, and this is by improving agriculture. Which means that if in the region, and their indeed analysis is based on the whole region, Israel is very small in the region, they come up with the suggestion that investing into improving of agriculture, and specifically irrigation, will lead to high performance of water use efficiency, increased crops, and the net marginal cost will be only a few cents per cubic meter. Again, all other measures will cost much more. We will not go through most of them, but I will go to the next one. And before I go to the next one, just to give you an example, what can be done by improving agricultural technology. This is a classical figure that many irrigation experts in Israel will show to farmers that are going to grow in the greenhouse with drip irrigation. And what you can see here, that in a farm where you want to grow with drip irrigation, vegetables, flowers, even trees, you would let each plant to have one dripper or more than one dripper, which will feed in directly if you want personally. And you may have a computerized system which will control how much water this plant will get every day, and if you want, it can get 8 times a day, and you can, through the computer, tell the system or tell your pumps how much of each nutrient to provide during the day. And as time would change, if there is knowledge, and there is knowledge which comes from the extension people, you can change the composition of the food that you feed your plant according to the knowledge. When the plant is young, the composition is 1, and then it grows, the composition is 2, and 3, and 4. And everything can be inserted in the computer, and indeed, very similar, excuse me for the similarity of feeding a baby. You know, that he needs the changes, and needs the ingredients to be changed, the amounts to be changed, everything can be controlled. And once you go into such systems, you can increase roughly the production by a factor of 10 or more as compared to the very simple systems that are used in the world. So this is just to give you an idea. But then the question, you see how complicated this looks like, and you need pressurized water. You need delivery of water to every place. This means infrastructure. This means somebody has to make the decision. We have to invest in infrastructure. We have to have the farmers. And indeed, then you need the technology, you need the knowledge, you need to show the farmers how to use it. You need people to be able to show the farmers how to use it. So this is not only technology, it's transfer of knowledge, transfer of information, and things like this to happen in many more regions in the world is a decision that has to be taken by government or by organizations, because somebody has to drive it. Farmers don't know even how to ask the questions. Somebody will come and tell them, help them, instruct them, then it can go. And there are some nice examples in the world that go like this. But in many places still, we are very, very far from being there. So actually, what this example shows you in very simple words that I was trying, these are many elements that can be implemented technologically wise, and I'm not going to describe, I just gave you a very rough. But each one, when I teach a class in terms of nutrient fertility, each one can take a few hours to explain. But you can guess that this knowledge exists, and it can be transferred to students, to agronomists, to farmers. Now, the other point in their analysis, I'm jumping on a few solutions, but I'm going to one solution that I want to stress. Again, they figured that a small percentage of water, the water gap, missing water, could be supplied to the farmer by the cost of 30 US cents if they will reuse urban water, domestic water. Take our sewage, treat it, send it back to agriculture. As you can see here, this in the MENA region and the Middle East and many North Africa and Middle East countries would save only 2-3%. Why? Because right now, the situation is such that more than 90% of the wastewater in most countries of the North Africa and Middle East are not well collected. And if you don't collect your wastewater, you cannot go and treat it. So this is one of the biggest obstacles to do it. And in Israel, the situation is that we collect all the water, 90% is sent to the farmers. But the proportion is just because you need the infrastructure and you need the decisions to be done. Indeed, the biggest contribution of the missing water will come from these two big lines here, and these are the reverse osmosis or the desalination. Desalination is expensive, but this is a solution that the world will have to go into it, but then you have to invest into it, and you have people to be ready for the investment, and you need the technology for that. I will jump because time is running, and I will just show you the whole concept that we are going about in Israel, which combines the water saving in agriculture, the reuse of reclaimed water, and desalination all together to make efficient use of water and then use the water for agriculture. This is a figure which shows you how water management and delivery is run in the developed countries in the world. Normally, we'll take the water from different resources, lakes, streams, aquifers, clear the water before we send it into our houses, and then people will use this water. And in all developed countries where you have good regulation, this wastewater, the sewage, will be taken to wastewater treatment plants according to regulation. And people know that they have to do it in all developed countries. And this wastewater, after proper treatment, would be either sent to groundwater reservoirs or to big water bodies where they do what would be called the solution is dilution. You take the treated wastewater under high standards and send it into your big streams. And again, after a while, this water will come back into our homes but be treated again. What we do differently, and this is again what I said in Western world, where developed countries, where there is regulation and people know that they have to do it. In many countries in the world, less developed countries, this is not done properly. What we do different in Israel is that we take 80% of the water which comes from the wastewater treatment plants and send it to agriculture use. So actually almost all the wastewater in Israel, instead of being sent back into water bodies or into large bodies like seas, and then some were recycled, it's sent directly to the farmers. And indeed the big question is, how sustainable would it be to use reclaimed, RWW is reclaimed wastewater. How sustainable will it be to use it for irrigation? If you don't do it under strict regulation, under high performance technology, then it's a problem. And there are many regions in the world where people know that they can save water by using reclaimed wastewater, but then the technologies that they use are very poor. There is no regulation, and then indeed you are going to be exposed to very big health problems. There are regulations for reclaimed wastewater use by the WHO, which are very different from the regulations in the US, from the regulations in Europe, from the regulations in Israel. They are much, much more tolerant because they know that people want to use this water. And this is one big issue, because if we really want to have sustainable use and safe use and healthy use, indeed regulation, and not only it's not enough to have regulation, you need to have the technology that can allow reuse of the wastewater for producing healthy foods. But in Israel it's not enough, because even though that we reuse the reclaimed wastewater, we don't have enough water. So we need additional water, otherwise we'll have a big deficit. And the additional water comes from desalination. So we take the water from the Mediterranean. We treat it by desalination, which is expensive. The desalinized water is sent into our homes. The water from our homes is sent into the wastewater treatment plants, and then it's sent to the farmers. So actually, by saving water in agriculture production, which started 50, 60 years ago, we saved a lot of water and we could produce high standard foods. But this was not enough. Then we switched into saving water by reusing reclaimed wastewater. And since this is not enough, we had to go into new sources like the desalination, and altogether this could help to maintain a good water situation and also high agricultural production. And this is a model which I can bring, but as you understand, it's very, very different from what's happening in many regions in the world. And I bring here a list of requirements or things that have to be done in order to make sure that you come to such a situation. You need to have very good research and development of agricultural technologies to be able to come to such a situation. You need to have good R&D work to be done in terms of the water treatment technology. Then you need to have very good knowledge and information transfer so that this high-tech knowledge will come down to the end users. Otherwise, the end users will not know what to do and how to go about it. then things are changing continuously. You need continuous regulatory and monitoring efforts. And then, altogether, the coordination of all these is proper management. Things will not be possible if you don't have good infrastructure. And again, infrastructure is the magic word, but infrastructure depends on so much decision making and investing making. And indeed, we come finally to the issue that you need governmental or organizational support that can help all these things to be done. Indeed, also economic drivers are important, because if you do all things properly, then it's very appealing to people to go into development of new technologies. One of the reasons that I come to Boston, Massachusetts, you have a lot of people very much interested in developing new technologies and then selling these technologies, which is a nice economic driver. But here we talk about food production, which comes much before the economic driver of developing new technologies. And indeed, societal involvement is important as well, if you have societal driving forces that push towards it. But again, the societal driving forces, they stay somewhere in the developed regions, and they are not yet down into the undeveloped regions. So I believe that all these together can help pushing into better water use efficiency, better food production, saving water for food production, producing the food in a much more efficient way. I brought some other examples of analysis made about India and China, but I think I gave you a good idea, and time is running, and I have also to deliver a presentation in Massachusetts University. So I think I gave you the picture of the main ideas that I wanted to, so I will end here, and I guess there might be some questions or remarks or whatever, so please, I'm ready for that.
The economist in me is curious to know what your take is on the role of prices for water in Israel. One would think that if it's such a big issue, as we know it is, that if it's properly priced, you give the signals to those who can develop the technology and deploy it, those who produce different agricultural products in a way that prices rise for meat relative to grains, and you change the diets for this. So prices have a lot of leverage over behaviors and technology development and deployment. So curious to hear sort of your perspective.
Okay.
Where the innovation on that front lies, rather than just the technology side.
Well, since it was recognized that water in Israel is a critical natural resource, water is measured everywhere. Every drop is measured, is metered. And people pay for the water. You may ask how the cost is estimated, right? Roughly, there was a decision that farmers will be subsidized. Water for agriculture costs less than water used in our homes. This is point number one. Then water used domestically, which is separately metered, has a cost which is not only the cost of the water, but also the cost of treating the waste. So roughly giving you some examples, a cubic meter for domestic use would be something like $2 per cubic meter, including all cost of bringing the water into your home and then taking back to the wastewater treatment plant. Farmers would pay for fresh water something like 30 something US dollar per cubic meter, which is much less, but they don't have to pay for the wastewater treatment, but they are exposed to quotas. Today, since we use more than 50% of our water in agriculture as wastewater, there are very tough quotas, and the farmers in each village or each region have the quota that they know that they cannot exceed. If they exceed the quota, then they pay 3, 4, 5 times. There are degrees. Pay much, much more from that. So they have an incentive to save fresh water. they pay for reclaimed wastewater something like 15 US cents for reclaimed wastewater, and this is the cost of the delivery only, because the cities or the producers of the wastewater by law are obliged to produce reclaimed wastewater under high regulation as part of the sanitation issue, not the. So these are the rules in the game, and with these rules, there's a good incentive for the farmers to save water, either mainly due to the issue of the water, and also through the driving force of using relatively cheap reclaimed wastewater. And I believe these more or less are dictating the game, but again, once you can see also here the marginal cost of water that was projected by this UN group was a few cents. If you do very well with your water, even if the water will cost 2 times more, you will go to smart crops, and you can produce things in a much more efficient way. And this project, they have projected 3-4 cents for a cubic meter. And another analysis done by McKinsey Group in India, they come up even with negative marginal cost, which means that if regions in India, they will learn to use high technology irrigation and fertilization with infrastructure, the cost will be negative, which means that the gain will be such that it will be very, very convenient to go for this. So roughly answering your question, I believe.
So taking a cue from there, you have talked about all the things that are important for this technology transfer. But if you think of some of the places like India, Africa, some places in China, I mean, some of those places where this might be needed the most, what is your assessment of how well this technology has been transferred, and what are the major showstoppers or stumbling blocks?
Well, there are regions in the world, like in China, where I've experienced it. There is a governmental driving force to bring down the technologies to the people, and they do it. And even there, I've shown you some examples where it was not done in the best way, but they do it. There are other places in the world where there is not a driving force, another governmental, organizational, and it's only if there are some voluntary groups that come down and help the village, which is nice. But once there is not an organized effort to push it, would it be governmental or organizational, but not only on a small village demonstration, because it's not efficient enough to do it just by demonstration. It's important to do it. So I believe that somehow being more involved in regions where this is needed, helping them, well, helping is who will help. I guess UN would have a very important role. I can tell you that we have in Israel, the Ministry of Foreign Affairs and the Ministry of Agriculture have a special unit called Mashav, which they reach many regions in the world and set up demonstration stations. But this is not enough if there is no a governmental or a large organizational driver to make it more efficient. Otherwise, you will have nice pictures, and I've seen nice pictures from the gentleman, the Indian gentleman that works with the IFC, and some others from small regions in the world. But the question is, how will it spread into the whole nation? My experience in Africa was that we had some projects in Africa, and people were excited about it, but then nothing was really to raise it up, because there is a need to push it in a very well-organized way so that many people will reach this kind of knowledge. The knowledge exists. One of the big issues is how to deliver it, how to convey to the end users. And in some regions of the world, it's not simple. I'm not sure I can solve that part. We can only provide examples and send delegates to do things in Africa, as I know we do. But
in the United States, there's a psychological aversion to using reclaimed water. directly. So was that a situation in Israel? And if it was, how was it overcome?
I'm not sure I got the point.
So in the U.S., there's a psychological aversion. So the general public feels that using reclaimed water directly for irrigation is somehow unhealthy or unsanitary.
Well, I spoke on technological means. You know, in my figure, I put a question here. How sustainable is it to use it for irrigation? Okay? And here I said the word regulation about 3, 5, maybe more times.
Sure.
Regulation has to be very strict here. Regulation refers to the sanitation issues. And I gave the example of the WHO, World Health Organization, as an example. They are tolerant in some parameters with 1, 2, 3 orders of magnitude as compared to what is done in Israel. Even when we compare our regulation to the regulation you have in the US, in some regions in the US, the regulations are less tolerant than we have, and some are more tolerant. But the example we have now is a relatively tough regulation. And since we have all the time also monitoring of the water resources, what's happening in the soil, monitoring of the food, I can say at this moment that there was no one report related to the use of reclaimed wastewater where somebody could say this problem came out of the use of reclaimed wastewater. It's not a guarantee. We all know that it's not a guarantee, but this is a situation. But the water that we are using is relatively high quality if you would compare it to what the WHO would allow of using reclaimed wastewater in the world. And this is a big issue when you want to go to less developed countries. And I guess that this group of experts that analyzed the situation in the Middle East and in North Africa, they were reluctant to push this direction too much ahead because they knew that regulation would not be strict enough. Therefore, they talk only about a few % of being able to solve this problem. But it's also a psychological problem in the US, and not only in the US, since we do have cooperation in the Middle East. For instance, Islam is not allowing reuse of reclaimed wastewater. So what they do in some places, they do a trick. They take, in Jordan, for instance, they take the reclaimed wastewater under good regulation or reasonable regulation. They mix it with a little bit of fresh water, and after they mix it with the fresh water, it's legitimate to use it. But there are cultures which really have a problem with it. And that's a cultural problem, nothing to do with the official or the regulatory work.
You know, it's a very interesting question. In Fishman's book about water, he relates the case of a city in Australia and running out of water, and the mayor proposes they use reclaimed wastewater. And the political campaign, she was run out of office, essentially. And they tried to make the point, well, the world has the same amount of water now that it always did. So all water is recycled water. But there's just a barrier. I mean, I guess given the situation in the Middle East, there's no choice. But at this particular point in Australia, they chose to build a pipeline that cost them 3 or 4 times as much and go to much more expensive solutions just because they couldn't get past that psychological barrier. So.
Yeah, but today also we have to remember that technologies are developing so fast that in Singapore, they drink reclaimed wastewater. And Singapore is very tough in regulation.
It's called new water.
Pardon?
New water, they call it, right? And government did a major advertising blitz, and then bottled water you could just get for free, and you could not taste any difference. It was as good.
So I believe that these technologies one day will be available worldwide, but right now the cost for specific membrane treatment to have this kind of water is high, and Singapore probably can allow it, and some other very little places in the world can allow it right now. Yeah, I'm afraid we will have one more.
Well, I had a quick question about greenhouse gas emissions. As you shift to an industrialized, highly technological system, you're probably more reliant on pumping, even as you're using less, in essence, less water for food production. And it seemed as though you were referring to the cost for example, desalination being expensive. But the other big cost that will loom large in these choices will be carbon emissions from the process of moving to this type of water management.
You mean the carbon emission from the process of desalination?
For example, or the pumping in this country.
Yeah, people sometimes really, it's very, very common to make these kinds of comparisons. Energy-wise, and I will shift now to cost, but cost would tell you the proportion of energy-wise. We talk now about these technologies to provide water at the cost about 55 US cents per cubic meter. 5 years ago, it would be $1.50 to $2 per cubic meter. The energy consumption for that would be in the order of magnitude of less than 5 cents. So just to give you the picture of 5 cents cost, now you can translate it to fuel that you buy to produce 1 liter. This is one option that I can provide you as an example. Now we can go to other options. When you go now and remove forest to have more land for growth, much worse. Would you be much more efficient in water using and water saving, including the use of desalination, because we must have this water. In some regions you cannot survive without this water. The issue is what we are trying to say. Before you go to desalination, do the steps that we started to do in Israel, and is to use water efficiently in terms of the irrigation. We have done much more than the desalination is doing today, because we use roughly 10 times more efficient today water use than 50 years ago. So per 1 drop, we produce roughly today 10 times more. So this is number 1 to do. But if you come to a situation where this is the situation we have now in Israel, where we don't have any other choices, this should be the last choice, desalination. But before you go to desalination, you have to go to all other options to materialize. It doesn't make any sense, and you can see it in Qatar. Since they have a lot of energy, they don't worry, and they can desalinize water, but they don't save enough water and food production. So where is the sense? But indeed, if you have plenty of energy to do it, so if you don't have other choices, you'll have to use desalination unless somebody will come up with some new inventions. But again, I think there is a misconcept of the energy cost of the desalination, and I just gave you the rough example of 5 cents, less than 10% of the total cost in terms of the energy cost. I believe that what it saves in terms of life saving, in terms of food production, it's nothing to compare. This is my idea about it.
I'm afraid your taxi is here.
Yeah.
So thank you so much.